Hello and welcome back to the Age of Gaming. In this video we will be covering the second mini program found in the first book of KIM called Mini Program B. In this program we will be filling 10 memory locations with all zeros. We should be able to get through this one pretty quickly and still have time to do the 3 exercises listed at the end of this program and go over some of the new addressing modes found here, as well as a few more valuable methods for troubleshooting any problems that you might run into in the future. So let's get started and load this program into memory, starting at memory address 200. But let's not forget to load the NMI and IRQ vectors, which we are told to load up every time that we fire up our KIM. So let's start by going to address 17FA. And go into data mode, and first we're going to put in 00, 1C, then we're going to skip the next 2, and then put again 00, 1C. Now we're ready to load our program. So let's go to address 0200, oops, 0200, and go into data mode and put A9, 0, plus A2, plus 09, 95, 30, CA, 10, plus FB, plus 00, and that's all there is to it. As you can see, there are only 5 opcodes in this program, so let's take a quick look at them right now and maybe explain each command in a little more detail later. The first opcode is LDA, which we know is load the accumulator or A register with 0. The next opcode is LDX, which will load the X register with a 9. Then we will start a loop at address 204 by using the STA or store A register at address 30 plus X. The next command is DEX or decrement the X register. Then we have the opcode BPL or branch if positive. So as long as X has not decremented past 0, it will continue to branch back to address 204 in our program. After X has decremented past 0, the program will continue out of the loop and end due to the break command at address 209. So let's sum this up quickly. We will load A with the value that we want stored in the 10 memory locations. In this case, the value is 00. Then, we will use X and the address specified by STA to determine which address spaces and how many address spaces will be loaded with the data. You may now have noticed that we are using 3 new machine language codes for LDA, A9, and LDX, A2, and STA, 95, than we used in mini program A, where we were using memory addresses 0010 and 0011 to load data into our registers. This time, LDA and LDX are using immediate addressing mode, which basically means we are giving LDA and LDX the actual values to load following the commands themselves. You may have also noticed the pound signs in front of those values, which are to be loaded in the assembly language portion of this program. That means that the following values are actual values to be loaded into the A and X registers. The next command, STA, also has a different machine language code associated to it. This is because it is being indexed with the value that we stored in the X register and not simply placed into a single memory address as before. This may seem a little complicated, but it is not. The command actually says sta store A, which we loaded earlier with the value of 00, starting at address 30 plus X. X was loaded with an immediate value of 9, so it will start by placing our zeros at address 39, and the next command will decrement the X by 1. After the opcode BPL will test the X to see if it's still positive. Now you may be asking yourself, why is there an FB that follows BPL, the BPL command? That is a good question. Branches can go forward or backwards. In this case, we are going backward 5 memory spaces from 209 back to 204. Now, if you are using an assembly language programmer, it will do all the work for you. If not, you will have to find a handy's 2 complement calendar lying around, or calculator lying around. Then you will have to find the 2's complement of 5 is FB. Another way is to start counting backwards from address 208, starting with FF at 208, FE at 207, FD at 206, FC at 205, and finally FB at 204. I know that does not sound like a lot of fun, but that is how branching works. Okay, let's press go and see if our program actually works. Now we can look at addresses 30 through 39 and see if our zeros were placed in all of these memory address locations. So address 0030, there's zeros. 5, 6, 7, 8, 9. So yeah, it looks like it worked. All right, now there are 3 simple exercises that we were asked to make some changes to see if we can make the program work. Before we continue on with a few more valuable methods for troubleshooting problems with your programs. Okay, the first exercise is, how can we change the value stored in all 10 memory locations to 55? Let's go to address 0200, and the first command is LDA, and that's where we loaded our zeros. Well, now they want 55 in there, so now let's press 55, and then go back to address 0200 and press go. Then we'll go to address 0030, and now we see all 55s in here. Okay, the next exercise, can we change the program to place the value 00 in location 0030 to just 0037? Okay, let's go back to address 0200, and that's where we LDA, and they want us to put 00 back in here. And next was LDX, which we had a 9, so this time we're just going to put a 07 in there. And then go back to address 0200 and press go again. Then go to address 030, 0030. There's our 0, 1, 2, 3, 4, 5, 6, 7. And so we were able to complete that exercise as well. Now, the final exercise is, can we change the program to put FF in location 00A0 to 00BF? Well, that's a little more challenging. Let's go back to address 0200. And there's our LDA. And this time we're going to put in the data FF. Next is load X with the 07. Well, if you subtract A0 from BF, you're going to come up with a value of 1F. So we're going to put 1F here for our value for X. And then we have, what is it, store A starting at 30. Well, we want to start at data mode A0. Then go to address 0200 and press go. That'll probably work a little better. 00A0. There's our FS. Where are we going to? BF. There we go. FF and all of those addresses. So that worked out fine. Now we're ready to learn a few programming tricks used when testing programs. We have already learned about the powerful tool of the single step mode when checking out programs. Although if you have a large loop in your program, single stepping all the way through it can be very difficult. So what can we do? In the mini program B, we currently have a small loop set up that would force us to go back 31 times before ending the program. That would be a lot of single stepping, and this is a very small loop. As X is being used to index the addressing space that we are filling, we can change the value of X while we are still single stepping through the program by accessing the X register at address 00F5. Here we can see that, let's go back to address 0200 and put it in single step mode, and we're going to press go, and we're going to start single stepping. Now we're loading that in, and you'll see it'll loop back to 204, back to 204 again. Let's go one more time, back to 204 again. Okay, now if we access, we go to address 00, what was it, F3, or F5 actually. Anyhow, it looks like we've decremented X down to 1C, which is basically a 28 in decimal. So we would have at least, 28 more times to go through this to finally get through this loop. What if we change the value of X while we are single stepping through the program to a value of 02? So we're at 1C, let's go ahead and change the value to 02 and press program counter, and then press go a few more times. There, it looped once, there it looped again, and we finally got out of our program without having to go through all 31 times that we were going to go through that loop. The only problem with doing this in this case is that we would not fill up all the memory addresses with the data that we wanted to fill. That is okay, we just wanted to see if the program is working. And if you run into a program with a large delay counter, this would be extremely helpful by bypassing the large delay by simply changing the register value that is being used to count down. Another helpful tool that can be used is the break command. By inserting a break command in the middle of a large program, you can quickly run through parts of the program that you already know are working and insert a break command where you would like to start single stepping through it. Let's give that a try. Let's change address 207. Let's see, address 0207, which is our branch of positive, to a break command. So data, changing that to a break command. Address 0200. Now this will wipe out the BPL, or the break on positive, but do not worry, we're going to be able to put it right back in after the system stops. We just wanted to run through the first part of the program and then single step from that point. Okay, now go back to the beginning of our program, and with the SST turned off, hit go. you will see that the program stops at 209, which tells you that the break command worked. We can now take a look at memory address 39 and see that the value that we loaded into A register has been stored here, and we can look at the X register at address 00F5 to see the X register was decremented by 1. So address 00F5, and you can see we're down to 08 now. Now go back to address 207 and place the BPL back in at address 207. So let's go to address 0207 and put our BPL instruction back in there. Now set the SST back on, and you are ready to single step through the rest of the program, checking the values to see if everything is working correctly. Another helpful instruction is the no-op or no operation EA, and that is exactly what it does, nothing. You can insert no-ops to take out an instruction that you do not want to use anymore, like a break command that you may have added into your program at various locations. What would happen if we replace DEX with a no-op at address 206? The program would continue to branch forever and never end. So let's go ahead and give that a try. Address 0206. And just want to double check here, 206 is our DEX, so we're going to put what in there, a no-op. So let's put an EA here, isn't it? E1, if that's correct. Go back to address 0200. Make sure we're in run mode and press go. And as you can see, everything went dark. In this case, when a program goes really sideways and the display goes dark for a long period of time and does not appear that the system will recover, that is when we are forced to use the stop key on your KIM-1. And if that does not seem to work, you can always press the RS or reset key. Well, that is it for the mini program B. We learned about immediate addressing as well as indexed addressing, and a few more troubleshooting tricks to help us resolve any problems that we may run into in the future. So that's it for now. Thank you for watching and have a great day.